Today's welcome to my video. I'm Avinash, and today the topic would be refraction of light through a prism. Let us consider a triangular glass prism. It has two triangular bases and three triangular lateral surfaces. These surfaces are inclined to each other, and the angle between these two lateral surfaces is called the angle of prism. Okay. First we should perform an experiment. In this experiment, ABC is the triangle, means the glass prism's one face, and one incident ray is coming through P and Q. It is hitting the point E. This is the point on the glass prism, and after point E, and then after refraction, it passes like a straight line, appearing like a straight line to us, but it is not straight as it is at an angle R, with respect to the normal, and it strikes point F, and further refraction, after refraction it emerges through a ray R and S, through a ray passing through R and S. Okay, and the angle that it makes with the normal is E. So this is known as I is known as angle of incidence, R is known as angle of refraction, E is known as angle of emitted angle of emitted. When we add, means when we stretch the PQ and RS ray, then they meet at a point G, and that angle is known as angle of deviation. This is that angle at which the original ray is deviated, means the incident ray is deviated from the emergent ray. These are the normals, N and M. N and N dash, M dash are the normals, and this is at the 90-degree angle. Dispersion of white light by a glass prism. Okay, we have to discuss the dispersion of white light by a glass prism. This is the glass prism, and this is when the white light strikes this point. After, means the reflection takes place, and it emerges in this way in the 7 different colors. The prism has probably split the incident white light into a band of colors. Generally, white light splits into 7 colors with gear. Note that the colors appear at two ends of the color band. They are seen as white, indigo, blue, green, yellow, orange, and red. As you can see on that figure also. That is known as Viv gear. It will help you to recommend the sequence of colors. The band of the colored components of a light beam is called its spectrum. You might not be able to see all the colors separately. When you see a rainbow, you don't see means you won't be able to, means what, differentiate all the 7 colors, but they are different. You can see that all are different, but you won't be able to differentiate it. As the rainbow, that is generally means it is seen in a very fainted way. Yet something makes each color distinct from the other. The splitting of light into its component colors is called spectrum. You have seen that white light is dispersed into 7 color components by a prism. Different colors of light bend through different angles, and the red light bends the least while the violet bends the most. The one of the reason is that the wavelength of red light is the highest while the wavelength of violet is the lowest. Thus the rays of each color emerge along different paths and thus become distinct. It is the band of colors that we see is called as dispersion. The band of distinct colors is known as dispersion. Dispersion of white light into 7 colors. Thus the rays of each color emerge along different paths and thus become distinct. Isaac Newton used the first glass prism to obtain the spectrum of sunlight. He tried to split the colors of spectrum of white light further by using another similar prism. Means he put the two prisms side by side, so that he tried it so that he can find other color also, but he didn't got any other colors. Then he performed another experiment, in which experiment means this allowed all the colors to this. Okay, just a second. However, he could not get in. He then placed a second identical prism in an inverted position. As you can see here also, A point and A point, they are put in an inverted way. When he put that into inverted way, when white light passed, it means the 7 colors are splitted, and when the 7 colors again put in the another prism which is placed in an inverted position, then you get the white light. So he performed this experiment. This observation gave Newton the idea that the sunlight is made up of 7 colors. Any light that gives a spectrum similar to that of sunlight is often referred to as white light. Okay. This is the means white light is nothing but a spectrum that is similar to that of sunlight. This is the diagram. This is the white light, and if we this is the angle of deviation for red. This will be angle of deviation for orange, and this should be the angle of deviation for the, okay, just a sec, this should be just a second. Oh, this should be angle of deviation for the violet light. Rainbow. Rainbow is a natural spectrum appearing in the sky after a rain shower. When the rain would be falling, when the not heavy rain but slight means drizzling of rain would be there, and the sun would be shining. Then we can see this phenomenon. This is beautiful phenomenon. It is caused by dispersion of sunlight by tiny water droplets present in the atmosphere. A rainbow is always formed in the direction opposite to that of sun, because as you can see also, if raindrops are falling, when the sun would be up in the opposite direction, then the rays will come from the sun, and it will scatter through the rain droplets, and the image will be formed backside only, no? Obviously, so one can't see the rainbow in the same side as the sun, because where will be the dispersion of white light? The water droplets act like small prisms. They refract and disperse the incident sunlight. They reflect it internally and finally refract it again when it comes out of the raindrop. Due to the dispersion of light and internal reflection, different colors reach the observer's eye. You can see a rainbow on a sunny day when you look at the sky through a waterfall or through a fountain when the sun behind you. Okay. You can also see a rainbow on a sunny day also, when you look at the sky through a waterfall or through a water fountain. Okay, you should try it with the sun behind you. This is the phenomenon of sunlight. When the sunlight appears, it reflects through the water drop. It hits the boundary of the water drop. Then further reflection takes place, and then it refracts from the emerges as the light ray from the interface of the water drop and hits our eye, and you can see the rainbow. This is the picture of a rainbow. Atmospheric refraction. Atmospheric refraction. You might have seen mirage when you would be going out in a very bright, hot, sunny day. Generally, it is seen on national highways when you pass through, and you can see that some distance away from you, you would see that there is a formation of lake or something, because you can see that there are water particles in the lake, view like lake. That is nothing but atmospheric refraction. That apparent random wavering or flickering of objects through a turbulent stream of hot air rising above a fire or a radiator. The air just above the fire becomes hotter than the air further up. If you have put something on a gas cooker, not a gas cooker, on a gas, then if you put something on a bowl, then that you can see that the heat rays is passing through it, coming out from it. That is nothing but this atmospheric refraction only. Since the physical conditions of the refracting medium are not stationary, the apparent position of the object as seen through the hot air fluctuates. This wavering is thus an effect of atmospheric refraction. on a small scale in our local environment. The twinkling of stars is a similar phenomenon on a much larger scale. This is the twinkling of stars. Next topic. The twinkling of a star is due to a atmospheric refraction of starlight. The starlight on entering the Earth's atmosphere undergoes refraction continuously before it reaches the Earth. When the light that is coming from the star is not the starlight, obviously, and the starlight that is entering the Earth's atmosphere undergoes refraction continuously till it reaches our eye. Means till reaching our eye, it must have refracted about million times. The atmospheric refraction occurs in a medium of gradually changing refractive index. Since the atmosphere bends starlight towards the normal, the apparent position of the star is slightly different from its actual position. And as the star is very far away from us, so that slight difference can be of a million or billion of kilometers also. The star appears slightly higher than its actual position. Okay, this is the actual position of star, but we can see that the star is here. And because of refractive index and all, the actual position, we can't see the actual position, but we see the apparent position. And this distance, it would be quite a billion kilometers also. Further, this apparent position of the star is not stationary, but keeps on changing slightly. Since the physical conditions of Earth's atmosphere are not stationary, as was the case since the stars are very distant, they approximately point-sized source objects. As the path of the rays of light coming from the star goes on varying slightly, the apparent position of the star fluctuates and the amount of starlight entering the eye flickers. For this reason only, since the stars are very distant and they approximate the point-sized source of light, they appear to us very point-sized. So the rays coming out from the star goes on varying slightly. The apparent position of the star fluctuates and the amount of starlight entering the eye flickers. The star sometimes appears brighter and at some other time fainter, which is the twinkling effect. Okay, when the star changes its position continuously, so there is a movement of stars. But so and as it is very twinkling, means as it is appeared as a very point sized, so that movement is only appears as the twinkling effect. Why don't planets twinkle? Because the planets are much closer to the Earth and thus are seen as extended sources. If we consider a planet as a collection of large number of point-sized particles, the total variation in the amount of light entering our eye from all individual point sources will average out to 0, thereby nullifying the twinkling effect. The planet are very close as compared to the stars, so the large number of point-sized objects, they are generally formed of a collection of a large number of point-sized sources, and the total variation in the amount of light entering our eye will average all out to 0. That's why it nullifies the twinkling effect. And so we see the twinkling of stars but not twinkling of planets. Advanced sunrise and sunset. Advanced sunrise means the sunrise or sunset that we see, that is about 2 minutes before the actual sunrise and the 2 minutes after the actual sunset. Because when the sunrise that we see, that is 2 minutes before the actual sunrise, and the sunset that we see, that is 2 minutes after the actual sunset, because of atmospheric refraction. By sunrise we mean the actual crossing of the horizon by the sun. Sunrise is what means when the sun pops up through the horizon, because we can see till the horizon, no, we can see below it. So sunrise is what? When the sun pops up through the horizon. And sunset is what? When the sun goes through the horizon. This is the image. This is the apparent position of the sun, and this is the horizon. When the sun would be below the horizon, this is a case of sunset. Okay, when the sun would be below the horizon, we would be seeing the sun at this position. So this is the apparent position, this is the observer, and this is the atmosphere. By the refraction, we are seeing it here. The time difference between actual sunset and apparent sunset is 2 minutes. The apparent flattening of the sun's disk at sunrise and sunset is due to the same phenomenon. Scattering of light. The interplay of light with objects around us give rise to several spectacular phenomena in nature. The blue color of the sky, why the sky looks blue and not any color. The color of water in deep sea, the reddening of the sun at sunrise and the sunset are some of the wonderful phenomena we are familiar with, but we don't know the actual reason. In this topic, we are going to see about, they clarify why they are so. You have learnt about scattering of light by colloidal particles. The path of the beam of light passing through a true solution is not visible. However, the path becomes visible through a colloidal solution where the size of the particles is relatively larger. Tyndall effect. The Earth's atmosphere is a heterogeneous mixture of minute particles. It is a heterogeneous mixture, not a homogeneous mixture. Homogeneous mixture means it would be of the particle would be very same, or they would be mixed so that they form the same structure, same mixture. Heterogeneous. It is the Earth is a heterogeneous mixture. These particles include smoke, tiny water droplets, suspended particles of dust, and molecules of air. When a beam of light strikes such fine particles, the path of the beam becomes visible. As you have read also in previous classes, in the previous class, that when you place a torch and when you pass it through a beaker containing distilled water, then you won't be able to see the path that traveled between the water. But when you place the distilled water and add some milk to it, then and if you put a torch, then you will see the whole distance traveled by the ray. But this will be not available. This will be not visible in case of water. But this is visible in case of the colloidal solutions, that is milk plus water. The light reaches us after being reflected diffusely by these particles. The phenomenon of scattering of light by the colloidal particles is give rise to Tyndall effect. This phenomenon is seen when a fine beam of sunlight enters a smoke-filled room through a small hole. If you are sitting in a room, closed room, and it's full of smoke, and if you pass a fine beam of sunlight through it, then you can see this effect. The scattering of light makes the particles visible. Tyndall effect can also be observed when the sunlight passes through a canopy of dense forest. Here the tiny water particles in the mist scatter light. In the canopy dense forest, would be some water particles, and these water particles in the mist scatter light. The color of the scattered light depends on the size of the scattering particles. Very fine particles scatter mainly blue light, while particles of larger size scatter particles of longer wavelengths. If the size of the scattering particles is large enough, then the scattered light may even appear white. Why the color of the sky is blue? The molecules of air and other fine particles in the atmosphere have size smaller than the wavelength of visible light. The molecules of air means the particle size of the molecules of air or the other fine particles like the smoke, what you have seen, dust, suspended particles of dust and molecules, their size is much smaller as compared to the wavelength of visible light. By visible light, I mean Vib gear. These are more effective in scattering light of shorter wavelength at the blue and then light of longer wavelength at the red. It can scatter the blue light, but it can't scatter red light, as the red light wavelength is much greater than compared to blue, because blue ranges is somewhere between 4000 to 5000, I guess, where this exceeds 7200 to be exactly approximate. The red light has a wavelength about 1.8 times greater than the blue light. Thus, when the sunlight passes through the atmosphere, the fine particles in the air scatter the blue color of shorter wavelength more strongly than the red. The scattered blue light enters our eyes, and thus we see the blue color of the sky. If the red means if the red wavelength of the red color would have been less as compared to blue, then we would have guessed why the color of the sky is red and not blue. Then we would have, means the question would be that. But as the blue's wavelength is very less as compared to red, so now the color of the sky is blue. Then the sky would have looked dark. The sky appears dark to passengers flying at very high altitudes, as scattering is not prominent at such heights. You might have observed that danger signal lights are red in color, because danger signals are red in color because that would be, as the red color doesn't scatter much, or it scatters very least, so it will be visible through, means at a very large distance. Do you know that why? The red is least scattered by fog or smoke, therefore it can be seen in the same color at a very long distance. Color of the sun at sunrise and sunset. Light from the sun near the horizon passes through thicker layers of air and larger distance in the Earth's atmosphere before reaching our eye. However, the light from the sun overhead would travel relatively shorter distance. At noon, the sun appears white, as only a little of blue and violet colors are scattered. As the distance of traveled by the suns when it is at the noon, it is as overhead, so the distance is very small as compared to the sun's distance at the horizon. Near the horizon, the most of the blue light and shorter wavelength are scattered away by the particles. Therefore, the light that reaches our eyes of longer wavelength, and in this case it is red, this gives rise to the reddish appearance of the sun. And here it is not bluish appearance, because the red's wavelength is much greater as compared to 1.8 times greater, to be exact, equal to the blue. So here it gives a reddish appearance to the sun and not bluish appearance. And see also here, the sun near the horizon, sun nearly overhead, and this is the horizon. Less blue light scattered and blue scattered away, sun appears reddish. This is us. That will be all for today. Thank you for watching my video, and do like it, share it and subscribe it. Thank you.